Hi, this is lecture second on the series that is UV-Vis absorption spectroscopy. So today in this lecture we will discuss about the transition energy levels or transition levels in any kind of molecule, so that we can understand the origin of energy levels or origin of absorption peaks. So we all know that, as we discussed in the last lecture, that molecular orbitals are of following types. One can be a sigma star, then it can be sigma pi star, then it can be non-bonding molecular orbital, and that is N, and then pi orbital, and then sigma orbitals. So in case of energy, if we discuss about their energy, so keep in mind this is the sigma. If you take a look of this diagram, then we can see that in this is the sigma bond, and that is this one, right? It is of lowest energy bonding molecular orbital, and it is represented by sigma BMO, and BMO means bonding molecular orbital. While this has lowest energy, and the pi orbitals having a higher energy than this sigma orbital, and we can see over here the energy level of a pi orbital is greater than the energy level of the sigma orbital. Likewise, the non-bonding is represented by N, and it is also represented by NBMO, non-bonding molecular orbitals, and its energy is greater than pi orbitals. Whereas the pi star is actually an anti-bonding molecular orbital, so it can be represented as pi ABMO, right? This is an anti-bonding molecular orbital, and this is also an anti-bonding molecular orbital of and it is represented as a sigma star. So this is bonding molecular orbital of sigma, and this is sigma star as the anti-bonding molecular orbital of the sigma bonding molecular orbitals, right? So if the possible transition and the energy orders, if we discuss about the possible transition in the molecules when they absorb energy, whether in the form of light, so it's a UV-Vis absorption spectroscopy. So we are talking about the absorption of a light by any kind of molecule. So if it is an organic molecule, so electron present in the sigma bonding molecular orbital, if it absorbs an energy, the amount of energy is higher, then electron can jump from this state to that state. That is a sigma star, right? So it's a huge amount of energy is required for this. It means we all know that energy is actually inversely proportional to a wavelength. So it means very short wavelength radiations have to be absorbed during this transition. So this the energy required during this, we represent it as HV1, and then there is another kind of and this is a high energy radiation. It's a very huge amount of energy is required to excite the electron from the sigma orbital to sigma star orbital. After this, the high amount of energy is required to excite electron from the non-bonding molecular orbital to the sigma star antibonding molecular orbital, like this energy. This energy is a very huge amount of energy, and it is less than the energy of the sigma, and we represent it as HV2. Then we have a pi and pi star orbitals. This has a low energy compared to N to sigma star, and we represented it as a HV3, right? So the last one, and the very small amount of energy is required to excite electron from the non-bonding molecular orbital to pi anti-star or pi anti-bonding molecular orbitals. So definitely we can see that the amount of energy required for this excitation would be higher, and the amount of energy required for this excitation would be very small. So we will discuss these excitations one by one, and which kind of molecules having these excitations or transition levels, and then that will help us to explain the absorption spectra of any organic molecule. So the first excitation is a sigma to sigma star excitation. So this excitation, normally the energy required or light required for this excitation is 120 to 170 nanometer. It means this is a UV region radiation. So you need a UV radiations to excite electron from sigma to sigma star. So you will get some signal in this region, and this kind of transition is actually occurs in all kind of saturated hydrocarbons which contains a sigma bond, like methane, ethane, propane, and so on. Any kind of organic molecule contains only sigma bond will show this transition. But this transition occurs in a light radiation of 120 to 170. Then the next transition is called as pi to pi star. Here we have a pi to pi star, and it requires an energy of 120 to 200 nanometers, and this occurs in unsaturated hydrocarbons. So like aromatic compounds, any kind of double, triple bonded molecules, then azo compounds, carbonyl group, etc. All these show this pi to pi star transition. So these are the two transitions we are normally observing in many kind of molecules. Like sigma is actually present in all kind of compounds having a sigma bond, while the pi to pi star transition occurs in a molecule which contains a pi bond, right? Double bond or triple bond. But what happened if we discuss about the absorption coefficient of these two kind of transition? So keep in mind, molecular absorption coefficient for pi to pi star is always very, very high. Almost absorption coefficient is equal to 10,000 when a molecule has a pi to pi star transition. And this pi to pi star transition, this is just because of the fact that the pi bonding molecular orbitals and pi star anti-bonding molecular orbitals both are actually existing in a same xz plane compared to the sigma orbitals. That sigma bonding molecular orbitals or anti-bonding molecular orbitals, they are present in a y and z plane which are perpendicular to each other. That's why electrons that are excited from sigma to sigma star is actually not in a same plane. That's why electronic excitation from the sigma to sigma star is quite of, it's difficult. So extent of electronic transition is lower in sigma to sigma star, while in pi to pi star this extent of molecular absorption would be very high. Why? Because these pi bonding molecular orbitals and pi star antibonding molecular orbitals are in a same plane. Like we can see over here, this is a pi, this is pi star bonding and anti-bonding. So in bonding case it is this one, while in the anti-bonding case the pi type of electronic transitions or type of orbitals would be like this. So in this case, so x pi and pi star, they are existing in the same plane. So on the same plane, electron excited from this to that region is quite easy and allowed. That's why the absorption coefficient of pi to pi star transition is very high. So we have like discussed in the previous slide that the electronic absorption, absorption of a light would be in this region 180 to 200 nanometer, which is towards the visible region, but still it is a UV region. So how can we extend this to a UV region? How can we observe a signal of pi to pi star in the UV region? So keep in mind, if you have conjugated pi electrons and they are normally excited at low energy due to the delocalization of electron, and that actually shifts the absorption spectra of a conjugated system from UV region to a visible region. For example, you have ethylene, and ethylene has this structure. It has a pi bond, pi electron and a sigma electron. So if we talk about pi electronic transition, pi to pi star, So it occurs at a wavelength of about 180 nanometer. But when we have a butadiene, that is a conjugated system, we know that the electron will shift here and these electrons will be shifted here. So it's a delocalized electronic system, and because of this delocalized electronic system, the absorption band is shifted towards the 217 nanometer. So there is a shift of about 37 nanometer just because of the conjugation. So if we get an extended conjugation, you will see that the molecule will start absorbing in the UV region, and your UV spectra will show a very intense peak of pi to pi star transition. Third type of electronic transition is N to pi star, and it normally occurs in 280 nanometer, and we have discussed in the last slide that this one is the electronic transition with the lowest energy. I mean, it requires a very low amount of energy. So if the energy is low, it means wavelength would be greater. So that's why the molecule will show absorption at a 280 nanometer. But this absorption is very weak transition, and it is forbidden transition. So it is forbidden and it is a weak. And why it is weak? Before discussing into the why it is weak, we just have to know about which kind of molecules show this N to pi star transition. So all those molecules which are unsaturated compounds having heteroatom and in their structure, and those heteroatoms must pair the unsaturated electron pairs. For example, you have this group, this is carbonyl group, right? We have this carbon sulfur double bond pi system, or you have a nitro group, etc. So all these contains these unshared electron pairs, and that are actually responsible for N to pi star transition. So in the case of N to pi star transition, there is a problem. And what kind of problem it is? That N to pi star transition, the symmetry of a bonding and a non-bonding molecular orbital, antibonding and non-bonding molecular orbital, is not same. Actually, these are perpendicular to each other. So it means this is a pi star orbital, right? So in the case of this is a pi star orbital, and this one is a non-bonding molecular orbital. These are perpendicular to each other. So the angle between these two would be 90 degree, and because of this 90 degree angle, it will not allow, or it hinders the overlapping, and that's why this is a weak transition and forbidden transition. So it means electron would not easily pass to that state. But what happens if because of the molecular vibration, if we provide energy to these molecules, so vibration will be starting, and that vibration is actually responsible to produce some kind of partial overlapping between these two perpendicular orbitals, and that allow a small transition or a transition to some extent. That's why you get a weak transition in this case. So thank you. So that is the end of this lecture, and in the next part we will start discussing the third type of transition, and that is it is N to sigma star. So we will discuss N to sigma star, and then some kind of like typical examples for it.